All right. So here's the connection, guys. Vectors and matrices are actually connected. A vector, in its component form, works just like a 1x2 matrix. So matrices are a matrix is just an array of numbers. That's it. And there are certain properties of matrices that we need to know. And so I'm going to introduce you to those properties, like adding, subtracting, and scalar multiplication. Now, multiplication for matrices works different than what you might expect. And it does relate to what's called the dot product of a vector, but we didn't talk about that. So I'm going to introduce you to multiplication of matrices, and that's actually the same as what we do with the dot product. So matrices can come in all different sizes. What's nice about a matrix is that it can be used to solve a system of linear equations of any size. You've only solved systems up to 3x3, right? 3 variables, 3 unknowns. So 3 equations, 3 variables. What we learn about matrices can be used on those to handle very simply and easily using technology. But it can be applied to, 100 variables with 100 equations if you wanted to. So matrices are very powerful. Linear algebra is a course that many engineers take at least one course in linear algebra, in which you learn some of the theory behind matrices, and then, of course, technology will do the calculations for you. But it's pretty common to at least do linear algebra 1, and that would be after your sequence of courses of calculus. So you're getting just the very beginnings of it. And I'll show you how to do some of this stuff on your calculator as well. So, element notation. An element, A, I, J, these are subscripts, the I and the J, and the I corresponds to the row number of the matrix, and the J corresponds to the column of the matrix. So, an element of a matrix, that could be typically a number, because a matrix is an array, usually of numbers here, but an element Aij is the number in the ith row in jth column. Notice they even use i's and j's just like we did with vectors. So the ith row, just like with a vector, and the jth column. So for example, looks like A12, it's not. A12 would be first row of this matrix, second column of this matrix, which would be the number -2. So it just tells you row and column. That's it. So that's how you identify a specific number in a matrix. Now, as I said earlier, the vectors we were studying had what we would call an order of 1, 2. That means 1 row, 2 columns. Very simple matrix, about as simple as you can get. Well, simplest would be a single number, which would be a 1-by-1 matrix. Okay? But the order of the matrix, we refer to a matrix of order m by n, where m represents the number of rows and n the number of columns. So this matrix down here, think about what the order of that matrix would be. Ask about this matrix. I'll let you write that down first. So a matrix of order m by n has m rows and n columns. So I asked the question, what is the element A32 of this particular matrix right here? So let's see. If you find the element A32, 81. Yes, it's the third row. 1, 2, 3. Second column. So that is 81. And then I asked the question, what is the order of A? The order is, we call this matrix A, and it's 3 by 3 rows and 4 columns here.
Oh, I see.
Yeah. Specifically, this is the element of the third row, second column. But the order of this would be 3 by 4. And order is very important when it comes to multiplication, because you can only multiply matrices of particular orders together. So there's rules that go with that, so that would be very important. All right, matrix addition and subtraction, I could tell you, just works just like vectors. It's really simple. You add or subtract the top left element with the top left element of the new matrix. Same thing with the, second column over. First row, second column. This element has to be added to or subtracted from its corresponding element. So we call that component-wise addition or subtraction. And then scalar multiplication simply means multiplying this number by each and every term in the matrix. So if I want to add those two matrices, really simple to do. First step would be do the scalar multiplication and just copy down the first matrix. So by scalar multiplication, this new matrix would be 3, negative 18, 33, and 0. You see how I got that? Just multiplying the 3 by each element. I want to draw a diagram or something. I don't know. Make a note. That's scalar multiplication, works just like vectors. And then addition is just like it would be with vectors, except that this is slightly larger. Each of these are 2 by 2. Sometimes we'll write the little order down here. But if I add these together to get a new matrix, what is my new matrix? Negative 5 plus 3 is negative 2. 1 plus negative 18, negative 17. 2 plus 33. 7 plus 0 is 7. So really simple to do. So that's addition. Let's do the next one together here just real quickly here. We'll do our scalar multiplication first and then subtract the 2. By the way, what's the order of each of these matrices? 3 by 2, good. So I've got 130. This is 10. And then negative 24 and 0. And then 28 and negative 34. And I'll keep the minus sign there just for fun. We could have multiplied through by negative 4 and then added them if you want to. Wouldn't matter. So this is negative 48. Negative 16, just moving across the rows. Negative, oops, and then I did exactly what I said I wasn't going to do. Let's try that again. So 4 times 12 is positive 48 and positive 16. And then I've got positive 36, positive, let's see, 168. And then negative 12 and 40 and 12, 52. And then I can subtract them component-wise. But like I said, you could have multiplied by the negative 4 and then just added them if you prefer. So my new 3 by 2 matrix, when I go to subtract these two, 130 minus 48, it's 82. 10 minus 16 is negative 6. Negative 24 minus 36 is negative 60. 0 minus 168 is negative 168. 28 minus 12 is 16. And negative 34 minus 52 is negative 86. Yeah, I should be adding 12. So 28 plus 12 is going to be 40. Thank you. I'm not doing my arithmetic correctly. That's what I'm doing. So 28 minus negative 12 is adding 12. I would probably multiply by the -4 and then just add them. Probably be less likely to make a mistake. The good news is that the calculator will do all of these operations for you once you enter the matrices in. And that's what you would do in life, because you would, use the technology to add, subtract, scalar, multiply these matrices. Also to solve these matrices to solve the system. Right, so here we have two matrices, A and B. They're both 2 by 2 matrices. And what's nice about matrix algebra is that you can refer to an entire array of numbers as a single letter. That's kind of nice. So I can call this matrix A, this matrix B, and then do these same operations on the matrices. So when I say -6 times B, what I mean is take -6 and multiply it by each element. So I have 6, 12, and then -6 times 8 is -48, and -6 times 5 is 30. Still off. So you can just multiply the -6 by each of those. 3A plus 2B would mean to multiply 3 by each element of A, which is -12, 3, 9, and 0. And then multiply 2 times each element of B, which is -2, -4, 16, and -10. And then go ahead and add the two matrices together, component-wise. So -12 plus -2 is -14. 3 plus -4 is -1. 9 plus 16 is 25, and 0 plus -10 is -10. So if matrices can be represented by single letters, it makes doing the matrix algebra much more efficient. Now, matrix multiplication. It would be nice if you could just multiply component-wise, but you cannot. You cannot multiply matrices component-wise. They don't operate that way. That's why this guy is here giving you a warning. Matrix multiplication is not as you think it might be. So it's not like addition and subtraction. Give this up a bit. To obtain the element Aij, we multiply the ith row by the first matrix by the jth column, of the second matrix, and then add. And that is equivalent to any of you who have done physics doing the dot products. You do the dot product for each row and column of the matrix. So I'll show you what that means. Have you guys done dot product? Then never mind. So the other thing that must be true is that the column of the first matrix and the row of the second, no, this thing is just not cooperating here. The column of the first matrix and the row of the second matrix when you're multiplying must match. Unfortunately, matrix multiplication is not commutative. So order does matter as opposed to in multiplying real numbers. 5 times 3 is 15, 3 times 5 is 15, we're all good. Not the case with matrix multiplication. Order does matter. And that's because the formula for it is a little more complicated. And I'll show you what it is. It's not hard. But there's a process that goes for multiplying matrices. I'll show you what it looks like in a theoretical sense here with 2 by 2 matrices, and then of course you could apply this to any size matrix. And you could go backwards and apply it to a 1 by 2 vector by a 2 by 1 vector. It's just a matter of taking the two vectors and writing one as a row and one as a column, and then you can apply this principle to it, and then you've learned the dot product. So you're learning the dot product today. So matrix multiplication for 2 by 2 matrices. It's not okay. Didn't write it on there. Okay. Try this one more time. just a little bit off. All right, so here's what I mean by taking the first row times of the first matrix by the first column of the second matrix to get our product. So it looks like this. So the element in the first row of the first matrix is A, right? And we're going to multiply that element by the first element of the first column of the second matrix. Okay. So it goes like this. AE. And then it says we're going to add it to the second element of the first row times the second element of the first column. So it's BG. So to get the top left element here, what we're going to do is take A times E and then add to it B times G. So it's this times that plus that times that, and that will give you the top left element. And then you continue that pattern. So then I go to, I'm going to take the first element of the first row of the first matrix times the first element of the second column and go A times F and then plus B times H. And that will give me the top right element. So it's kind of a A times F plus B times H. If you go down to the second row, you're going to do this row, maybe I'll circle this, times this column. Okay? So it's going to go C times E plus D times G. And what you'll notice is that in the columns here, they're going to match here. And you'll see that first element in each of those is from the first row and then the second row. Then I'm going to take and multiply CD times FG. And this is what I mean when I say it's the same as the dot product. If this was one vector, CD, the other vector, you'd just write it this way, vertically. And then this one term here would be what you get for the dot product of two vectors. So we have CF plus DH. So that's our formula written out for a 2 by 2. Of course, you could do that formula if you wanted for any size matrix, but the process is the same. Usually we just understand the process and then apply it to any size matrix. It's kind of hard to describe in words. So if I have matrix A times B, here's what it would look like. Matrix A times B is 2, 3, 4, 7 times 0, 1, 5, 6. And I'm going to write on here, this is 2 by 2 and 2 by 2. The first thing we should ask is, does the column of the first matrix match the row of the second matrix? In other words, are those inner terms of the order equal? If they are, then you can multiply. If they are not, you cannot multiply these matrices. Okay, so first thing I'm going to do to get the top left is I'm going to go row times column. Boom, boom. So 2 times 0 plus 3 times 5 will give me my top left element. 2 times 0, 3 times 5. And then the second column, first row, would be 2 times 1 plus 3 times 6. So 2 times 1, 3 times 6. Then I go to the second row and multiply that by the first column. So it'll be 4 times 0
plus 7 times 5, yeah. And what you should notice here is that these line up. That's kind of your check. And then finally the second row times the second column, which would be 4 times 1 plus 7 times 6. So once again, what you see that I have in parentheses, those should be matching up if you kept with the pattern. So this equals the new 2 by 2 matrix, and it is 0 plus 15 is 15, 2 plus 18 is 20, 0 plus 35 is 35, 4 plus 42 is 46. So 15, 20, 35, 46. So I had told you earlier that matrices under multiplication are not commutative. So when I take A times B, this is the matrix I get. When I do B times A, I'm going to get something different. Okay. Most of the time. Well, at least in this case. There's certain matrices where you get the same thing. But in general, they are not commutative. So, looks like this. We have 0, 1, 5, 6 times 2, 3, 4, 7. So it changes the order. So first row times first column would be 0 times 2 plus 1 times 4. First row times the second column would be 0 times 3 plus 1 times 7. And then second row times the first column would be 5 times 2 plus 6 times 4. And then second row, second column would be 5 times 3 plus 6 times 7. And once again, just make sure that what you have in parentheses here matches up. That'll help you to see that you've multiplied correctly. And I will get a different matrix. The top left of this matrix, 0 plus 4 is 4. 0 plus 7 is 7. 10 and 24 is 34. 15 and 42 is 57. So a completely different matrix. 4, 7, 34, 57. All right. Turn it over to that. Sometimes it's harder to multiply a 1 by sort of matrix than it is a 2 by 2 matrices. 2 by 2 matrices are nice. They're square matrices. They're ones that are nice to work with. They are, here's the parallel. 2 by 2 matrix would be equivalent to having a system of 2 linear equations with 2 unknowns, like an x and a y. As a matter of fact, we'll do that later, but creating a matrix equation out of something like 5x plus 3y equals 10 over 4x minus 2y equals 7. Create a matrix out of that and solve it completely on the calculator using matrix algebra. So that's not super, that's not going to help you be much more efficient, but then you take that method to 3 by 3, and it is. You guys solved 3 by 3s last year, I think, probably by substitution. Combination substitution. Did you do like an x, y, z? Solve for x, y, and z. Here's 3 equations, 3 unknowns. Your matrices can take care of that, just like that. You'll find x, y, and z without going through that whole process. And actually, you'll find it to be useful at times in calculus. You'll find that you end up solving some 3 by 3s next year. All right. Given that A equals, by the way, what's the dimension? What's the order of this one, or dimensions of this? How many rows? How many columns? This is 1 by 3. And this is 3 by 1. Okay. So if I go to do A times B, I've got a 1 by 3 times a 3 by 1. Will the multiplication work for this? we've got 3 by 1. If you look here at the dimensions, those inner dimensions match, so this will work. By the way, if you take out these inner dimensions, it will tell you what your solution matrix size will be. So if you remove these, what's my solution matrix size going to be? If you take these out, so it's like remove these and you're left with a 1 by 1. Okay, 1 by 1. So it'll just be one matrix here. It's negative 1 times 7 plus negative 4 times 2 plus 3 times negative 6. Which equals negative 7 minus 8 is negative 15. Minus 18 more is negative 33. So A times B works great. We have a 1 by 3 by a 3 by 1. No problem there. Now, when I go to multiply B times A, here's what I've got. I've got 7 to negative 6. And I'm multiplying it by negative 1, negative 4, and 3. Do you see the problem with this one? Sorry, I gotta try this again. This is a 3 by 1, and this is a 1 by 3. Look here, 3 by 1. Write that right. 3 by 1, 1 by 3. Okay, that one's okay. 3 by 1 and 1 by 3. So, how is this one going to differ from the one I just did? It's going to be a 3 by 3, yeah. So it's quite different doing A times B versus B times A. So let's go ahead and see if I can do the multiplication here. If this board's going to cooperate, it's having a tough time. All right. So we're going to go row times column. So the top, it's kind of nice to know what to expect. So we have 7 times negative 1. And then what's the next term going to be? 7 times negative 1. And then we have 7 times negative 4. And then we have 7 times 3. And that'll be my top row. And then I have 2 times negative 1, 2 times negative 4, and 2 times 3. And then I have negative 6 times each of those same 3 elements. So my 3 by 3 matrix is negative 7, negative 28, and 21. And then negative 2, negative 8, 6, and 6, 24, negative 18. So a very different matrix, multiplying A times B versus B times A. All right. Number 10. Can you tell me, based on order, what size the new matrix will be on number 10? It will be 3 by... I'm not sure if I'm here. So we have a 3 by 2, and this is a 2 by 4. It'll be 3 by 4, yeah? It's a little wider than it is going up and down. So 3 by 2 and a 2 by 4. We can multiply them. These match. So I've got row times column. So 4 times 1 plus 2 times 0. Need a little more room here. Then I have 4 times 2 plus 2 times 2. So first row times second column. 4 times 2 plus 2 times 2. Then I do first row times third column. 4 times 3 plus 2 times negative 1. And the last one is first row times fourth column. 4 times 4 plus 2 times 6. It's going to be 3 by 4. So the next row, second row times first column, is 1 times 1. This thing just will not cooperate. So 1 times 1 plus 3 times 0. And you can look up here at the previous one and match those up as you go. So then I have 1 times 2 plus 3 times 2. Then I have 1 times 3 plus 3 times negative 1. And then 1 times 4 plus 3 times 6. And then we're going to take the third row times each of those same columns. So we'll have a negative 1 times 1 and a 7 times 0. So it'll be negative 1 and 7 multiplied by each of those same numbers. So negative 1 times 2 plus 7 times 2, negative 1 times 3 plus 7 times negative 1, and negative 1 times 4 plus 7 times 6. So going straight across, we've got 4, and then 8 plus 4 is 12. 12 minus 2 is 10. And 16 plus 12 is 28. And then 1 plus 0 is 1. And then 2 plus 6 is 8. 3 minus 3 is 0. 4 plus 18 is 22. So 1, 8, 0, 22. And then the last row is negative 1. Negative 2 plus 14 is 12. Negative 3 and negative 7 is negative 10. Negative 4 and 42 would be 38. It should be negative 1, 12, negative 10, and 38. Didn't leave any room for 11. We won't need it. Here's why. This is a 2 by 4, and this is a 3 by 2. So if you look at the inner dimensions, the columns of the first matrix and the rows of the second, we know that we have, your calculator would actually call this a dimension mismatch. A dim mismatch would be its abbreviation. So that's probably a good way to describe it. This is a dimension mismatch, cannot be multiplied. So dimension mismatch cannot multiply. Right. Then a little connection to what we may have done back in geometry with transformations. It says the given quadrilateral can be expressed by the matrix Q. So you'll see on there negative 2, negative 3. This needs to be connected here. So negative 2, negative 3, you see that right here? Negative 2, negative 3? That's the xy coordinate. That's this coordinate down here. 2 left, 3 down. -1, 2 is this coordinate. 3, 4 is this one. And 1, -2 is this one. So these are the x, y, if you will, coordinates of that quadrilateral. So what would be the matrix representing a quadrilateral shifted 4 right and 1 down? So how could we shift this 4 right and 1 down? If this is x, this is the x row, and this is the y row. Shifting 4 right would mean adding 4 to the entire x row. You with me? And shifting 1 down would mean subtracting 1 from the entire y row. So what I could do is take -2, -1, 3, and 1, and -3, 2, 4, and -2. And add to that, if I want to shift each x coordinate 4 right, I just need to add 4 to each x coordinate. And if I want to shift each y coordinate 1 down, I just need to take away 1 from each of those. So my new matrix would be -2 plus 4 is 2, -1 plus 4 is 3, 3 plus 4 is 7, and 1 plus 4 is 5. And on the bottom I have -4. 2 minus 1 is 1. 4 minus 1 is 3. And -2 minus 1 is -3. So a quadrilateral shifted 4 right and 1 down would have the coordinates 2, -4. So there's a new coordinate. 3, 1. 7, 3. Somewhere up here. And then 5, -3. Doesn't quite look right because I couldn't go over quite enough, but that is my shifted matrix. Okay, B says shrink the quad to half its perimeter. We call that a dilation. Dilation. I don't know if you remember that, but dilation. So I would just take 1/2 of matrix Q. So I'd be taking half of each of these elements. So it'd be -1, -0.5, 1.5, 0.5, and then -1.5, 1, 2, and -1. So half of Q, -1, -1.5 would be about right here. -0.51 would be about right here. 1.52 about right here. And 0.5 comma -1 would be right here. So I have this little guy right here that is half the size of the one I started with. This is one of the applications of matrices, is that whole connection to geometric transformations, to transform geometric shapes or any shapes. And then you can apply these different properties of matrices to them. It says let B equal -1, 0, 0, 1. Find BQ. So find BQ. So B equals -1, 0, 0, 1. Does anybody have any guess as to what this might do to the matrix Q in terms of transformations? Any guesses? So what we're doing is making an x coordinate negative and a y coordinate keeping it the same. So changing each x-coordinate from its whatever its sign is to its opposite, and leaving the y-coordinate the same. You have any idea which transformation that might be? Yeah, you're demonstrating it. It is a flip. You see which it's a flip over if you change all the x-coordinates sign. I can see Rachel over there going like this. It's a flip over the y is what it does. So it's this is 2 by 2, and this is 2 by 4. So my new matrix will be 2 by 4. Hide it underneath this. And -1 times -2 would be, I think we can do this without writing it all out. I think you can do it. -1 times -2 is 2, plus 0 is going to be 2. 1 plus 0 is 1. You may not be ready to do this yet, but it can be done. You can kind of go in your head, do the two parts. -1 times 3 is -3, plus 0 is -3. See if I've done it correctly. I'll check what I did earlier. -1 times 1 is -1, plus 0 is -1. So my first row should be 2, 1, -3, -1. That wasn't too bad because that 0 there, huh? Same thing here. 0 plus -3 is -3. 0 plus 2 is 2. 0 times 3 is 0, plus 4 is 4. And then 0 plus -2 is -2. So this would be reflected over the y-axis. Reflected over the y-axis.